the eight the eight spectrum, yeah, or seven spectrum over there. So now there are electromagnetic wave of short wavelength, all right. Electromagnetic wave, they don't have material medium. Then they have or they don't need the material medium for their propagation. Number two of properties that they have a very small ionizing power. Then number three is that they have high penetrating power. Number four is that they are not deflected by magnetic field, unlike beta particle is deflected. Then number five, they move at high speed of light. Then number six, they are electrically neutral. I've said all of that. So those are the properties of your alpha, beta, and gamma particles. So, like I said, there are two kinds of reaction we have. All right, there are two kinds of reaction we have in radioactivity. Two kinds of nuclear reaction. Now, the first nuclear reaction in physics is called. So the first kinds of nuclear reaction in physics, all right, is called nuclear fusion. Right, nuclear fusion. So aside from nuclear fusion, we have nuclear fission. All right, those are the two reactions that exist. Unlike in inorganic chemistry, where we have the types of reaction to be combination reaction, catalytic reaction, and all of that. So here we have two. The first one is what we call nuclear reaction. We have two nuclear reaction. So there are two nuclear reactions we have. So the first nuclear reaction, number one, we have nuclear fission, and we have nuclear fusion. All right, so I'll differentiate between the two. Fusion. Now, for nuclear fission is actually the combination of two or more lighter nuclei to form a heavy nucleus. Like the combination of the allotropes of hydrogen. All right, 1H1. In allotropes of hydrogen, we have 1H1 to be protium. This protium. All right, we have 2H1 to be deuterium. This deuterium is what we call the heavy hydrogen, and we have 3H1 to be called the tritium. All right, these can combine together. So if you have 1H1 protium combining with maybe the tritium, it will yield, all right, helium 4-2. This is an example of what? Of a nuclear fusion. All right, this is not fission, this is fusion. All right, so two or more lighter nuclei are combining together to form a heavy nucleus. This is a lighter nuclei, these are not lighter nuclei. So the process, all right, of nuclear reaction whereby two or more lighter nuclei combines together to form a heavy nucleus with a release of heavy amount of energy is what we call a nuclear fusion. Why nuclear fission now? Which is the second one? Nuclear fission is defined as the breaking down or the disintegration of a heavy nucleus into two or more lighter nuclei. Like uranium has an atomic number of 92 and is 235. I think if you disintegrate it, what is going to happen is that at the end you have thorium of 90 and 234. So at the end you have this plus Q. Plus Q there means plus energy, because anytime there's a nuclear reaction, there's always a release of energy. So you have 234 here, 90. What is left? You can put what? 2H1 there. Alright, I think helium 42 can go in this like manner. One is 234, this 90. So what can go? Can alpha particle go or 1H1? You can use this 2H1, or we can use 1H1 as the value, so that this should be 235 and this, I think this 92. So the value here is supposed to be for thorium. Thorium should have the mass number of 230. Is it 2? Yeah, 233 thereabouts, because it has an allotrope. So you have helium 2 and 4. Alright, so that it will balance 90 and 2. So I'm just trying to use an element as an example to form a nuclear fusion. So this is the heavy nucleus that was disintegrated out, that was broken down, and two or more lighter nuclei will form, plus the release of what? An amount of what? Or certain amount of energy. Okay, so those are the two kinds of reaction we have on the board: nuclear fusion and nuclear fission. So let's move on. So peradventure I give a question, alright. Let's say I give uranium, all right, of 292 and 235 disintegrating to maybe an element unknown, and I'm asked to calculate for, let's say, thorium, all right, 90. Let me just put values there: x plus 1H1. All right, let me put Z here. All right, and I say calculate for the mass number, this Z, the mass number and the atomic number of this element respectively. What are you going to do? These 235, all right, is going to be 235 is equal to X. Here is the mass number, that is X plus what is here is 1, is 1. This will give you the what? The mass number, and the symbol for the mass number is A. All right, so at the end you are going to be having 235 is equal to X plus 1. So that is 235 minus 1 is equal to X. Then A is equal to 234. No, that means at the end your mass number, all right, A is equal to what? Is equal to 234. But if you want to determine the Z here, the atomic number, you come back to the denominator, which is 92 is equal to what is there? Z, then plus 1. Then what do we have? We have 92 minus 1 is equal to Z, which is 92 minus 1 will give us 91 is equal to Z, which is the atomic number, A number. So we have Z is equal to 91. So at the end, our element, all right, X is rewritten as, let's say it's X that is here, we write it as, and A is here. We write at the value of A to now what? What's the value of A we calculated when we solve for the up? The upside, our A gave us the value of the 234. So we have 234. Why the value here is what? Is 91. Alright, so that's how to find your element. You can use atomic number and the mass number of a calculating the reaction to determine the position of the element. So if you are seeing 234 and X, so you can determine the position of the element in the periodic table. That is how to go about those ones. So that is the first fundamental analogy that you need to understand in radioactivity, how your reaction works and how your movement, all right, the practice of your particles work from alpha, beta, then the gamma. Then what are the uses of radioactivity? We use radioactivity in physiotherapy, all right, that is used for treatment of cancerous, all right, cells in medicine. We use it in industry also to detect wears of parts in machine like gearbox, all right. We also use it to trace in industry to detect. We use to detect leaks in pipes. We use to we use it in tracer to study the working of plants and animals. We also use it in agriculture to develop effective fertilizer and insecticide. We use it in radio sterilization. Radio sterilization is used to sterilize fabric in textile industry and in medical supplies as bacteria. All right. We also use it in carbon dating. All right. Those are the uses of what? Of radioactivity. Radiotherapy used as tracer in industry to detect waste and of parts of machine. All right, we use it to detect leaks in pipe. Use it as tracer to study the work or working of plant and animal. Using agriculture to develop effective fertilizers and insecticides. We also use it in radio sterilization. I said sterilization is used to sterilize fabric in textile industry. All right, and in medical supplies as bacteria to destroy on exposure. We can use it to destroy bacteria on exposure to rays. Then it is also used in carbon dating. All right, so those are the uses of radioactivity. Then the major part here is that there are two different things I want us to consider after this. All right, then we would have a fundamental analogy on what radioactivity stands for and how to calculate for half-life and the life. So this is the introductory video. So in the next video you will see the part of how your half-life and decay constant and the law of radioactive element works. So thanks for watching and God bless you.